Hey everybody, welcome to today's lecture. Today's lecture is on dynamics. Now, in the last lecture, we did this analysis of a system that was at rest, right? So we looked at how do we balance out the joint forces versus the forces acting on the end effector, and how do we do some calculations around that. Now, the thing about that was it was actually possible because the system was at rest, right? None of that would have made sense if the system was moving. Okay, so in this lecture, we're going to look at modeling some dynamical systems. What do I mean by dynamical systems? That's just systems that change over time, right? So if you've got some variables that describe the state of the system, those variables are changing over time. Okay. Um, when I say modeling, that means we're going to try to find some relation between the forces and the uh, or the position and the acceleration of these state variables. Okay. Um, Now, when we when we talk about forces, I'm just going to introduce some forces that you've probably seen before. So introduce is probably the wrong word. Some of it in high school physics, maybe you did university physics or applied mathematics even. The first one I'm going to talk about is the most commonly known one, F equals ma. Force equals mass times acceleration, and using the sort of dot notation that we used in the previous lectures, that would be F equals mx dot dot, right? Because we're taking the second derivative of x, where x is our state variable, so that means the acceleration of our state variable. So F equals ma is the same as F equals mx dot dot. Okay. Some other forces that are important is we've got a drag force, which is F equals minus cx dot. And basically what that says is that the amount of drag is proportional to the speed of to the velocity of the variable, but in the opposite direction. And we've got a spring force, F equals minus kx. And what that's saying is that if I've got a mass attached to a spring, then there's a force acting in the inverse direction of the position of the item. So basically, if you picture that there's a spring and a mass on the end, if I pull the mass in some direction, that means there's going to be a force acting in the opposite direction, which is basically the spring pulling on the item. And the magnitude of that force is going to be proportional to how much I pull the mass away from the spring. Okay, so that's all very well, but how do we actually go about working with or getting these forces when we have some description of the system? Well, a very important component in here is something called the Lagrangian, and the Lagrangian is defined as the kinetic energy minus the potential energy of the system. I'd like to give you a common sense explanation of why that's the case, but I've never found one. If you do manage to come up with one or find one, I'd be very interested to hear it. But generally, it's just something that pops up out of the math, right? If you're trying to find a nice, concise mathematical expression for the joint forces, you end up with this Lagrangian term, and it happens to be the kinetic energy minus the potential energy. So there are ways to describe it in math, but not really in common sense, right? Now, the Lagrangian is a function of the state of the system and its velocity, right? So the state and the derivative of the state. And it is equal to the kinetic energy minus the potential energy. The kinetic energy we refer to as Q dot, meaning that the kinetic energy is a function of the state and velocity, minus the potential energy. And the potential energy is also a function of the state and the velocity. Okay, so we call the kinetic energy T and the potential energy V. When we've got this expression, what that allows us to do is calculate the joint forces. So the forces acting, or the torques basically acting on our joints, or on our control points, if we can put it that way. And basically, we say that tau of j is equal to the derivative with respect to time of the partial derivative of the Lagrangian with respect to the velocity minus the partial derivative of the Lagrangian with respect to the position. Okay, so the when for the Lagrangian, the partial derivative with respect to the velocity, we still then take the derivative with respect to time. And what we subtract from it is the partial derivative of the Lagrangian with respect to state. And that gives us the torque acting on that variable, if we can put it that way. So in this study of dynamics, we're generally going to be looking at uncontrolled systems. So what that means is we're looking at systems which have no external control applied to them. What do I mean by that? So, an object can kind of move just because these are the forces that are acting on it in the world, or it can move because we applied some control, we pushed it, or we, applied a force in some direction. Now, what we're looking at here is systems in which we are not applying any control, okay? Meaning the forces that we apply, these taus, are all going to be zero. Again, future lectures, you'll look at optimal control and you'll look at how to actually apply control to these things. But for now, we're looking at uncontrolled dynamical systems. So we get this equation equal to zero. Okay, so that was just definitions and garbage. This will start to make a bit more sense when we look at some examples. So the simplest example is to just look at a falling mass. So we've got a mass, so a ball of mass m, and it's falling. Okay. Now, if you remember from any previous physics or applied maths course, kinetic energy is equal to half mv squared. Okay, v is the velocity of the system. So with our dot notation, we can say T equals half mx dot squared. Okay, so the kinetic energy of the system, we have a very clear formula for. And what's the potential energy of the system? Well, in this case, the only potential energy it has is the potential energy due to gravity, which you might remember from any, again, previous physics or anything as mgh, right? It's the mass of the object times the gravitational force times the height of the object. In this case, our state variable is x, so x represents the height, so we can say that the potential energy V is mgx. Okay. Now, the Lagrangian, we said, was equal to T minus V, right? So it's equal to half mx dot squared minus mgx. Okay, it's just this minus this. And we said that we were looking at uncontrolled systems. In this case, we're looking at a system where the mass is just falling, right? We're not doing anything to this ball. So that means the force that's being applied, tau, is zero. So when we look at this equation over here, we'd say that this equals zero, right? So if we plug that in here, we get that the derivative with respect to time of the partial derivative of the Lagrangian with respect to velocity minus the partial derivative of the Lagrangian with respect to the position is equal to zero. Okay, that's just from our unjustified math. I've chosen not to justify it. It's pretty unpleasant. Feel free to look it up online if you are interested in the derivation. We're not going to care about that for this lecture. But we've got this equation. So the cool thing is we've got all of these terms, right? We can plug them in. We can figure this out. So if we look at this Lagrangian and this equation, when we calculate this term, we're looking at the partial derivative of the Lagrangian with respect to the term q dot, which in this case is x dot. Okay. Now, because it's a partial derivative, we can take this x dot as the variable, and when we take the derivative, we're going to get mx dot, right? So it's half mx dot squared, and x dot is our variable. We end up with mx dot. And for this term, there's no x dot in it. So the whole thing is just a constant, okay? So we end up with zero, right? So we can say that the whole partial derivative then becomes mx dot. For this term, this partial derivative of the Lagrangian with respect to state, this term doesn't have any x variable in it, right? It doesn't have a term for the state. So it just becomes zero. And we're left with minus mgx. And if we take the partial derivative with respect to x, we get minus mg. Okay, so we've got these two terms. But the Lagrangian says that we further have to take this term and find the derivative with respect to time. Okay, so if we take the derivative with respect to time of mx dot, we get mx dot dot. Okay, straightforward. We're taking the derivative of speed and getting acceleration. Okay, so we end up with this equation: mx dot 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 plus mg equals 0. So that's the same as saying x dot dot equals minus g. Okay, and that's quite interesting because that's saying that our acceleration is equal to minus g, meaning g acting in the downward direction, and that's great because that's what the term is. That's exactly what we were expecting g to be. So I mean that wasn't a particularly useful analysis in any way, but what it did do is it confirmed that the analysis works. Right, we got something we already know to be true out of the system. Okay, and I think it was quite an interesting way to sort of look at how to model this thing. Now, that may have seemed like a lot of work. You may have been thinking like, yeesh, that I had to find the kinetic energy, I had to find the potential energy, I had to do L equals that, I had to take this thing, and it was kind of unpleasant. So why do it? Well, anytime you see someone doing this, it's because every other way is harder. Okay, so when you think about the difficulty involved in doing this analysis, or even in working with the Lagrangian, and it's not particularly difficult, but there is some unpleasantness to it. The important thing is try to think of how you would model this if you were unaware that there was such a thing as the Lagrangian, and then you'll appreciate the Lagrangian, right? Because suddenly, like you can actually model this. The other thing I just want to emphasize is that in all of this, I mean, when we figured out the kinetic energy, we just plugged it in. We didn't think about it. When we talked about the gravitational potential energy, we didn't think about it. We just plugged it in. This was just a formula. This is the result we know, so we just plugged it in. We took these partial derivatives and we plugged it in, and we got here. And what I'm trying to indicate by that is, if you had to figure out what insight we used on any of these steps, you'd be like, we didn't use any. And insight is really the expensive thing, right? We're computer scientists, so we know when there's an algorithm, great, well, that's easy. We can follow an algorithm. And so what this Lagrangian analysis allows us to do is define an algorithm that we can just follow to get the properties of the dynamical system. So that's pretty cool. Okay, so let's take it to a bit of a more interesting example, and we'll look at a mass on a spring. Okay, so in this case, we've got this mass that's attached to the spring, and obviously if we pull it here, we get more force pulling this way, and we'll get the sort of forces acting this way, pulling the ball in this direction, or towards the spring, if I can put it that way. So let's do this analysis. We know that the Lagrangian is t minus v, so we go, well, what's t? T is half mv squared. It just always is. We don't even have to think about that. It's just half mv squared, so it's half mx dot squared, and we just don't care. Okay, the potential energy of a mass being pulled by a spring is half kx squared, where k is the spring constant, which specifies the sort of hardness of the spring, how much it will pull in relation. So it depends on the spring. We're going to leave it as k for now, or forever, I guess. So v equals half kx squared. That's the potential energy of spring, and it's, again, not a result we're going to try to bother with. It's just known. So if we take the Lagrangian, then it's half mx dot squared minus half kx squared, right? It's just t minus v. So again, if we looked at that, we didn't have to think about it. Neither of these terms were things we had to think about. We just had to look them up and plug them in. Okay, then if we say we want to get to this equation, we're going to take the partial derivative of the Lagrangian with respect to the velocity. And if we take the partial derivative of the Lagrangian with respect to velocity, again, this term has no velocity component, so we can just look at this one, and we'll get mx dot. Similarly, if we're looking at the partial derivative of the Lagrangian with respect to the state, we get only this term, because this one has nothing to do with the state. It only cares about the velocity. So we're going to end up here with minus kx. Okay, it's that 2 getting multiplied by the minus half, and we end up with minus kx. Then we have to take this term and take the derivative with respect to time. So we end up with where we had mx dot, it becomes mx dot dot. So now this entire equation becomes mx dot dot minus kx equals 0. So mx dot dot plus kx equals 0. Okay. And this is a differential equation, and solving it, getting anywhere requires you to solve the differential equation, which, if you guys have done any DE courses, is often incredibly unpleasant to do analytically. In this case, we're lucky that this particular form of equation has got an analytical solution. So we can say that, if we know that a differential equation that has the form x dot dot plus omega naught squared of x, omega naught squared times x equals 0. So if we've got that form, then the solution is this thing, right? X of t, meaning the state at time t, is equal to x subscript naught, meaning our initial position, times cos of omega naught t plus the velocity, the initial velocity, over omega. That shouldn't be w, it should be omega, sine omega naught of t. Okay, so the so yeah, that's my customary mistake. That should be omega naught, not w, times sine of omega naught of t. But this closed form solution again is just a known thing. We're not gonna, we don't care. Someone else has found that solution. We're happy with it. And we had this function. We had mx dot dot plus kx equals 0, right? So we can restate that as x dot dot plus k over mx equals 0 by dividing by m throughout. And that brings it into this form, right? Where our omega naught is equal to the square root of k over m. And when we've got that, we can plug that omega naught in there, and that'll mean that we can at any point just plug in our initial conditions and our current time, and we can get the state at any time. Okay, so that's pretty cool, because it means that if we've got a mass on a spring, we didn't have to do much thinking again, right? Like, all of this was kind of we just plug it in and we get somewhere. And what we end up with is an equation that describes the position of the mass at any time, which is pretty great. Okay, so let's look at another example, which is again a quite popular example. Is we can look at a pendulum. For a pendulum, we'll have a number of variables. We have the mass of the ball that is at the bottom of the pendulum. We have the length of the string from which the pendulum is hanging, and we have this angle theta, which is, the pendulum's busy swinging, and so we need to represent the state of the swing, right? So that's the theta. And if we've got this, we can then calculate the position of our system as L sine theta, comma, minus L cos theta. And that just comes out of the trigonometry, right? So our sort of x and y positions are just based on the x position is based on this sine of theta, which will give us this, and the height is based on the cos of theta, which is this, right? And if we want to know our velocity, then we just need to take the derivative of the position with respect to time. And the only variable here that's changing over time, the mass is not changing, the length is not changing, it's our angle that's changing, right? So that means we take the derivative with respect to time, and we end up with L theta cos theta, comma L theta dot cos theta, comma L theta dot sine theta. And that's just from the chain rule. So we've got our velocity now. And that's pretty cool. That's pretty cool because our kinetic energy T is equal to half mv squared. Okay, so if we've got our velocity, we can figure out our kinetic energy. Now, one interesting thing here is that we've got sort of an x velocity and a y velocity. But what we really need is a velocity, right? A full velocity, if we can put it that way. And what we're going to rely on here is Pythagoras. Because we've got a velocity this way and a velocity this way, we can calculate the sort of velocity on the hypotenuse, if we put it that way. So we can say that v squared is equal to L theta dot cos theta squared plus L theta dot sine theta squared. Basically these two terms, because that's our x and y and that's our r, right, in the sort of Pythagoras formula. And then because we've got a cos squared and a sine squared, we can just get rid of that. It can become L theta dot L squared theta dot squared cos theta squared plus L squared theta dot squared sine theta squared, and then the cos squared plus sine squared can come out, which is equal to 1, and so we just end up with L squared theta dot squared. Okay, so again, that makes our kinetic energy easy. It'll just be half m L squared theta dot squared. Our potential energy, in this system, the potential energy is entirely due to gravity, right? So that means it's going to be defined by minus mg h, where h is the height of our system, and the height is L cos of theta. So, that's from here. We've got this mgh. So h is minus L cos of theta, and we end up with minus mgl cos of theta. And that gives us our potential energy. So then our Lagrangian, which is T minus V, just becomes half m L squared theta dot squared plus mgl cos theta. Okay, so it's because that's just from plugging it in, T minus V, we get that. Okay, so now that's our Lagrangian, and we want to get it into this form, so we do the same things we did before. We take the partial derivative with respect to the velocity and the partial derivative with respect to the state, and then furthermore we take the derivative with respect to time of this partial derivative, and we end up with this thing, ml squared theta dot dot plus mgl sine theta equals 0. Okay, and the m is common, so we can get rid of it. We get L theta dot dot plus g sine theta equals 0. And that's our differential equation. Then we've got to solve it. Okay, so that's, again, kind of unpleasant. Solving d is not something I find fun, although there are lots of people who do find it incredibly fun, and hopefully you're one of those. So, because we all need people to do that, so we don't have to. But one thing we can do is, for small oscillations, we can use something called small angle approximation, which basically says that for small angles, sine of theta is approximately equal to theta. Okay, you can sort of picture it if you picture a sine curve. At the start, it looks like it's sort of going diagonally. Before it starts waving, it looks like it's just going diagonally. And in that spell, where it's going diagonally, you'd get that sine theta equals theta, right? So and for that case, we can then take this equation and turn it into theta dot dot plus g over L theta equals 0. Okay, and the cool thing about that is that fits into our form that we have an analytical solution for. So the cool thing about that is that then we can just plug in this and we can get something. We can get an equation of this form, and that'll mean we can describe where the pendulum is at any point in time, which is pretty great. Again, considering it was quite an algorithmic approach with number. If you try and think of how you'd figure out where the mass is at any point in time, if you didn't have the Lagrangian, it starts to become pretty unpleasant. But let's look at something even more unpleasant. Let's say we're at a pendulum on a cart. So there's a cart over here, and there's a pendulum swinging from it. but the cart is on wheels on this plane. And what happens is, as the pendulum moves, as it swings, it kind of pulls the cart along. Okay, so if the pendulum swings that way, then the sort of momentum of the pendulum ends up pulling the cart, and when it swings back, the momentum ends up pulling the cart back the other way. So this is quite an unpleasant system to think about if you don't have the Lagrangian. But if you do, well, then we can just do the same analysis we always do, with some minor differences. Well, so in this case, there's now two variables. There's theta, which describes the angle, right, the swing of the pendulum. But there's also x, because we said the pendulum can pull the cart, which means we need to keep track of where the cart is. Okay, so there's a position of the cart, and then there's a position of the mass which is relative to the cart. So if we wanted to figure out what the position of the mass is, we'd say that it's equal to x plus L sine theta, comma, minus L cos theta, right? It's exactly the same as the one for the pendulum that was hanging from a fixed point, except that now we need another variable over here because the cart can move. Okay, and depending where the cart is, it becomes x plus L sine theta, comma, minus L cos theta. Okay, and now we have to take the derivative with respect to time. So we end up with x dot plus L theta dot cos theta, comma, L theta dot sine theta. Okay, so that was just from differentiating these two things. And since we've got the velocity, we can say that t equals half mv squared. And in this case, we need to express the mv squared of this one and the mv squared of this one, right? We've got two masses, and they both have kinetic energy, okay, because they're both moving. So the kinetic energy of this mass is just half mv squared, and v is x dot, because x is the position of this mass, so we get half mv squared, right? And the kinetic energy of this one is also half mv squared, but with a different m, right? It's the little m. The mass of this one here is big M, and the mass of this one is little m. I clearly forgot to put the m in there, and I will do that before I upload the slides. But so, yeah, this one here is half capital M x dot squared, and this one here is half m, and now v squared. For this thing, we do the same Pythagorean thing we did for the previous one, and we say that it's half m, and then it's x dot plus L theta dot cos theta squared plus L theta dot sine theta squared, right? So we've got our kinetic energy, and our potential energy again is only due to the position of the height of the pendulum, so it's minus mgl cos theta. And that's exactly the same as it was for the for this pendulum. For that pendulum example, it makes no difference that it's hanging from a movable cart rather than from a fixed point. So our Lagrangian, which is t minus v, is then this unpleasant expression, and it's just this thing minus this thing, right? So nothing too scary there, but it kind of looks horrific. And so we've got this Lagrangian, and we want to get it into this form, so we do the same thing we've done so many times before. But here's the interesting thing. This thing says it's the derivative with respect to the velocity, and this one is the partial derivative with respect to the state. But there's the subscript j, and what that's trying to indicate is that this is true for all state variables. Okay, so when we take this equation, we can apply it to every state variable in turn, and it'll always be equal to 0. So in that case, that means we have that the derivative of the partial derivative with respect to x dot minus the partial derivative with respect to x is equal to 0, right? That's the same form we've seen before. And the same thing, but with the variable theta, is also equal to 0. So both of these are true. So that's one of the reasons I wanted to look at this example, is just because we have two variables where previously we had only one state variable. And if we do take those, if we do sort of fill in this, expand this equation, we end up with big M plus little m x dot dot plus ml theta dot dot cos theta minus ml theta dot squared sine theta equals 0. And that's our first equation that came from the partial derivative with respect to x. And then for the one for theta, we end up with theta dot dot plus x dot dot over L cos theta plus g over L sine theta equals 0. And, that's just, you can give it a try yourself. That's what you'll come up with. And I'm not even going to try to solve those. In real life, most of the time, these differential equations are not easy to solve analytically. In fact, generally, I'm not even sure they're possible to solve analytically in most cases. Some of them are, of course, but in most cases, no. And most cases don't even try. So you end up using an ODE solver, in something like MATLAB, and it'll just solve it numerically. Okay. And in general, for this course, you can kind of, if you're ending up somewhere here, that's fine, right? We don't actually sort of care that much that you solve the DE in terms of the coursework, because like I say, in real life, you're gonna do it numerically, and you're gonna, more than that, you're actually gonna get a computer to solve it numerically. You're not gonna go to that point. But so the cool thing is, so we ended up with this, and we're going to get a computer to solve the DE, and that's going to give us an expression that'll describe theta at time t and x at time t. And if we looked at this system, if we didn't have that, and we had, look, this pendulum is pulling this cart, and this cart is pushing this pendulum, and the pendulum is swinging, and when it swings the other way, it's counteracting the force that it pulls. Like if you tried to do this from a sort of basic understanding of the forces or anything like that, you'd just be like, no, this is utterly impossible. But actually, none of the individual steps here were hard, right? And by following them, we end up with a solution to our system. So, sort of the philosophical thing I want you to take from that is that, when you see math like this, it's tempting to go, geez, that math is hard and I hate it. But the important thing is it's a tool, right? So like, it might seem hard to put a screw in with a screwdriver, but if you didn't have the screwdriver and you just screw it in with your hands, it would be much harder, right? So there's no getting away from the fact that you have to solve these systems. There's no getting away from the fact that you have to be able to predict what the state variables are going to look like over time. So given that you have to do it, this tool actually makes it way easier than if you didn't have it. Okay, thank you all for listening to me. And I hope you enjoyed it.